Hello, everyone. I am Anil Gürses. I'm a fourth-year PhD student at North Carolina State University. I'm working with AERPAW, and today I'll be talking about what AERPAW is, what we are capable of, and I will do a quick demo with AERPAW development environment, also known as digital twin. So probably you have seen this picture from others. Like it's very common these days. Everyone comes up with volley of that. As you know, there is a big gap between the universities and national laboratory labs and the companies from the research perspective and the production perspective. So programmable testbeds, which AERPAW is basically located between them. So we allow researchers and students or companies to test their thing on a programmable testbed, and basically close the gap between, as you see on the picture. So NSF started a program called Platforms for Advanced Wireless Research. They funded 4 testbeds across the United States. Each of them has its own unique features. AERPAW is one of them. Our unique feature is unmanned aerial vehicles and mobility. And other testbeds have features from software-defined networks to massive MIMO, millimeter wave, rural broadband. So yeah, and we are located in Raleigh, North Carolina. So this is the team and partners. We are partnered with Wireless Research Center, Mississippi State University, RNC, Purdue University, University of South Carolina. We have quite a team. So Dr. Sikito you see over there is my advisor. We have people working on the UAV development side, RF side, SDR development side. We have a variety of people working on different areas. So AERPAW platform, this is the general overview of the AERPAW platform. We have 2 sites. One of them is located inside the campus, Centennial campus of North Carolina State University. And we have, as of now, we have 3 fixed nodes, which are towers. And we can run some experiments in the campus, but we cannot fly drones over there. And we have Lake Wheeler site, which is a farm that has 5 fixed nodes, which are towers, and each of them are equipped with software-defined radios, commercial base stations, respective RF front ends, keysight RF sensors, and other radio equipments. And in Lake Wheeler field, we can fly drones, we can drive rovers, and we can basically mimic anything related to the rural area there. And we have FCC Spectrum license and FAA permissions to fly the drone with SDRs. So you can see some example pictures on the bottom, the experiments we have carried on. As I said, we have 5 fixed node towers. They are all marked as red over there. And now, yeah, as I mentioned, on each of the fixed nodes we have software-defined radios ranging from B205 Mini to B210, X310, and N310. Also, we have Ericsson 4G, 5G commercial base stations, LoRa gateways, keysight RF sensors, and many more. And in terms of the vehicles, we have LM UAV, which is large AERPAW multicopter. We have small UAV. We have UGV, also known as rover, and we also have helikite. So each of the vehicle can carry a portable node, which I brought with me here. And portable nodes are carrying a host PC and also a software-defined radio, or based on the needs, it can carry a CUTS UE or other type of hardware you see. And there are many research examples. As you can see, we don't touch the experiments, so you have the option to pick what kind of application you want to do. You have the SDRs, you have the hardware we have specified here. So you program the vehicles, you program the radios, and it's a very unique feature that AERPAW has. And also I've added the user manual and project website on the bottom. Yeah, this is the large AERPAW multicopter. As you can see, it's quite big, and probably have seen it in the demo booth. We have the portable node on the bottom, and we usually attach a portable node on the bottom of the UAV or and connect it to the batteries allocated in the drone. So as you can see, we have FAA beacons, batteries, the GPS receivers. GPS receivers are supported with RTCM updates, which is provided through RTK base station we have in the fixed node. And we have cellular modem on the portable node, which allow AERPAW operator to connect to a vehicle and observe, monitor the hardware we have. And yeah, there are other equipments we have. So I got this question from others a lot. AERPAW drones are made by the AERPAW personnel, and they are all custom built. It's not something you can buy from market. We have our own CNC routing, and we milled everything from scratch. We designed our own PCBs, so it's quite a unique multicopter. So, and this is the small portable node we have. We use this mostly to carry CUTS UEs. I forgot to mention that the LEM can fly around 45 minutes with the payload, and yeah, this is the small multicopter we have, and most of the time it carries a CUTS UE because it's small and you don't have to, have a quadcopter. So this is the UGV we have. This is our actually previous UGV. It carries the portable node on the top, and it has the GPS receiver and the controller on the bottom. We drive this on the field, so you can also program the UGV. They're all using the same firmware. As I mentioned, we also have HeliKite as a vehicle. So we put the same portable node on HeliKite and bring it to some higher altitudes and get measurements from there. Team did some measurements during the NC State Pekapalooza event. We gathered some LT logs, 5G logs, as far as I know. And also they did some LoRa measurements, and you can see that there are some dots on the picture, middle bottom. Those are the some points that we gathered measurements. And yeah, so the main problem is at the heart of AERPAW, programmable radios on programmable vehicles. Most of the time you have access to software-defined radios, but what about the programmable vehicles? Because in the lab setup, everything is easy. You can make the attachment procedure like working flawlessly. But what happens when you take it to the outside? This is where AERPAW comes into the picture. We allow users to program the vehicles. And we do that in a way that we have our custom library to make users program the vehicles. So we basically not allow every command they issue, because they can just bring down the drone. So we don't want that. And yeah, that was for the testbed part. But another unique feature we have is the digital twin. So how that happens? So assuming that you're an experimenter, you came to AERPAW, and then you got into the web portal, you created a project, choose development resources, like how many portable nodes you want, how many, what kind of SDR, what kind of vehicles you want, like what kind of fixed node you want in the real world. And after you choose your resources in the development in the portal, it creates Docker containers. And after creating the Docker containers, we give SSH access to you, and you can program the vehicles, radios, and also the higher level application on the digital twin. We don't have any physical hardware connected to the digital twin. It's all happening in the software level. Therefore, it's a very unique feature. We are not using ZMQ or anything like that. We have, which I've mentioned in a second, we have a custom software for that. And then after you are done with your experiment in digital twin, we move your containers without touching any piece of software you wrote or any line of your code. And we just seamlessly transfer your experiment into the testbed mode. And it runs on a real hardware, and we fly it. And there are AERPAW operators that observe and monitor the experiment. So making sure that everything is running smoothly, there is no problem in the radio side or on the host PC side. And there is also a pilot, which is a safety pilot, who checks everything, the flight is going according to the plan, or it's not violating any rules. If something happens during the flight, the person over there, the pilot, safety pilot over there, takes the control, overrides the control, and takes back the drone. And then after completing the testbed experiment, we put your experiment back to the digital twin. So you analyze the results, and then if you want to do another round of testbed experiment, you submit your experiment to testbed again. So this is kind of a general picture of the digital twin. As I mentioned, you have containers, and in that containers, the yellow boxes you see, those are developed by the experimenter, basically you. We have example for each of those boxes. For example, for vehicle control application, you can have some autonomous software, or you can have a pre-planned trajectory. And on the traffic generator side, it's like AERPAW, ping, things like that. On the radio software side, you can choose srsRAN, which you should, and then you can use OAI, GNU Radio, and other Python scripts. And at the bottom, we have virtual radios. Virtual radios we mimic the SDRs. You basically use virtual USRPs, and then it's connected to the channel emulator I have developed, and it's also connected to the vehicle emulator we have. We have emulation of everything. We have emulation of channel, emulation of vehicle, and emulation of the radio. With this way, you can program it as it in a real world. So it's a seamless, as I said, it's a seamless transaction for experimenters and the operators, and you are doing all of these in IQ level, so which is quite unique. To again recapture the overview, so we can describe it as like this: portal and configuration. We deploy your experiment as like the Dockers in a Docker. As you can see, I've tried to do some fancy figure over there. And then you can start with simulation if you want, but it comes with disadvantages because you need to implement it again for the hardware. Or you can just go to the digital twin, develop your thing, and then after you are done with that, if you want, we can move it to the sandbox, which is not yet available for the experimenters right now. Sandbox is just a hardware-in-the-loop channel emulator in a server room. So instead of immediately going into the testbed environment, we check your experiment in a closed environment with the hardware-in-the-loop channel emulator, make sure that it works OK with the real hardware and other impairments happening on the hardware. And then we move it to the testbed, and there is an infinite loop until you are done with your experiment. Yeah, this is what we envision with the digital twin, starting from the left arrow, starting from an idea to production. You start development in digital twin, move it to the real world testing, and bring it back to the development environment, the digital twin environment again, and it continues until you are done with your, until you are satisfied with your product. So there are some extensions we have. We are thinking like emulating other things like vision radar and putting other things on the overall environment, like for AI stuff, things like that. And yeah, we also had a student challenge in the digital twin and the real testbed. Last year, the students from other universities came to the AERPAW, created experiments, and we had a rover in a random location in the field transmitting some waveform, and we expected users, the competitors, to allocate the signal source and get close as much as possible. So it was a great example of how to use the digital twin and our testbed environment. Everybody enjoyed, and we had sponsors. They got some awards and things like that, and it was quite a good introduction for them. So as I mentioned, I will do a live demo. I hope it will work as expected. You know how these things happen. You always say it was working on my local, so fingers crossed. So any questions before the demo? Okay. Sure.
Have you done any performance benchmarking
Yeah, we had. They're actually all like we compared the like the SNR results, like the especially for example, giving since we are in srsRAN workshop, we have even compared like srsRAN performance on digital twin and in real world. So to see how much discrepancy happening on the metrics and things like that. So yeah, we have done some benchmarking over the channel emulator, like how much bandwidth it can run on, and yeah. Yeah, it's all in the website, and yeah. If you want, we can talk more after the talk. Any more questions?
So when you run srsRAN in digital twin,
Yeah.
what are you using in place of the front end?
What?
What are you using in place of the radio front end? Do you use or?
We are using virtual USRP. It's a thing that I've developed. So it's a USRP, but virtual. I will show it in the demo. Any other questions? Okay. Oh, please. Yes, it does. For example, yeah, they can do that. For example, we have a script that does some spectrum monitoring that shifts over the spectrum and gathers some IQ data. So while we are running like srsRAN G node B or E node B, it gathers some IQ samples through the PyUHD.
What kind of distance range can you get with the drones? How far can they fly?
With srsRAN, we were able to get like close to 400. But I should mention that we have RF amplifiers and filters for that, so not like with just bare SDRs.
400 meters.
Yeah, meters. Yeah, I still not get used to the feet and things like that. You can do that. So we only ran like AERPAW or ping or MGen. But there are other applications you can use, or you can just stream a video using the srsRAN running on the bottom. So we are not just allowing you to do like specific networking experiments or like just vehicle experiments. You can, by using our examples like srsRAN 4G or 5G, you can deploy your high-level application and consider like measuring or analyzing different level of the srsRAN, like physical layer, make layer, or any other metric you want to look.
Did you see any connection drop or any throughput, hyper throughput drop?
Yeah, we do see that because it's a moving vehicle, so there are lots of not lots of changes, but there are some changes happening on the channel while you move the device. If you get for example, if you go further, it will just disconnect and reconnect back. But if you are running multiple fixed nodes, you can also do handover between the towers using the srsRAN. Any other questions? Okay. So I think everyone can see my screen right now. I'll just briefly go over the portal, like what are the steps. Then I'll go over the user manual, and then I'll do the demo. So this is the main page that welcomes you when you get to the web portal. When you first come to the AERPAW, you create a project, and after you create the project, like here, you can make it public or you can make it private. And then after you create the project, you create an experiment for that project. And you give the names and description for it. And then this is the screen that welcomes you to what kind of resources you want to pick, what kind of vehicles you want to use, and to submit it to development environment, emulation environment, or sandbox environment or testbed environment. So this is how you add the resources. CC1 stands for Centennial Campus. LPN stands for Large Portable Node, which is here. And you can basically choose multiple of it. And then we have Lake-Wheeler nodes, SPN nodes like Android phone or LoRa or Coactel. And then after you pick them, this is the screen you see. And then here there is a thing called not vehicle, which is the type of your vehicle. So if you click modify, you can rename it, and you can pick what kind of vehicle you want to use. And this changes affects the digital twin because the emulated vehicle changes. So yeah, these are the options you have, and then you click on save, and you have your resources here. And then after you do that, you click on initiate development, and then it creates the Docker containers for you. So after you create the experiment and it's being deployed to the AERPAW environment, it creates two files for you. One of them is manifest.txt, and the other one is the VPN profile, which allows you to connect to your experiment. So let me quickly show you what the manifest file look like. Can everyone see the fonts, or should I make it bigger? Is this good? Okay. I think everyone can see this, right? So it basically lists the IP addresses you have, the portable also the OEO console, which is a console to control the vehicle and other things, like basically your experiment. So before going into this, I'll also mention about the user manual. So we have quite a big user manual that includes lots of tutorials and overview of the system and things like that, and even how to create like a project experiment, all these details. And for example, here is a vehicle example, like pre-plan trajectory. You use Q-ground control to design a flight trajectory, or a trajectory for the vehicle. And then after you create this file, you copy it to your experiment, and then you run the example script you provide here, the pre-plan trajectory, and you follow the instructions here, and it just allows you to run the vehicle. And then on the radio side, we have experiments, as you can see on the from here, like ranging from srsRAN, OAI, GNU Radio, UHD, Python API experiments, and more. And then here, if you go into the details, we have different versions of srsRAN examples. And then it basically gives you instructions to how to configure your srsRAN experiment and things like that. And also for the traffic side, we have ping, AERPAW, and also mgen, but I think it's not written on this version of user manual. And you can basically use these instructions to deploy your application. And now, let's go to the terminal and see. I have 4 terminals here. Each of them responds to a node. And let me quickly show which node is response to what. So, and then here, so on the top left we have portable node 1 UAV. On the right one we have operator experiment oversight console, which I will show you very quickly. And then we have portable node 2 UAV on the bottom left, and we have fixed node, which is tower, on the right. So it's basically the replica of the system we have in the real world. Now it's time to launch the OEO console, but before that, I'll just reset my environment, which resets the vehicle and channel emulators. So there's a progress bar on the bottom. It will reset in a second. So, by the way, I created this experiment before the presentation to just not wait for 5 minutes to deploy, but it only takes 5 minutes to deploy your experiment. Okay, I think it's almost done. Yep, it's done. So this is the OEO console. Let me make it bigger so you can see it easily. So it shows 3 of the nodes and the screens they have, and it gives some information about like the altitude of the vehicle and the mode the vehicle in and the GPS status. And you can add more information to this console, and you can arm the vehicles from here. And then on the portable node side, let's check what kind of files we have here. So we have a reset script, and we have start experiment script and stop experiment script. These are the scripts that the operators are using when we move it to the testbed. So you need to put your experiment into these scripts. It comes with a template. So in here, as you can see, I have radio, traffic, and vehicle scripts running here. As you can see on the bottom. I hope everyone can see it. Please let me know if you can see it. And then if we go to the example experiments here. So we have radio, traffic, vehicle, as I said. And if we go inside each of them, you will see a bunch of applications like ranging from srsRAN IoT, srsRAN MIMO, srsRAN 5G, things like that. We have all of these things given for our experimenters. So it's just an example template for the experimenters. If you don't want to use them, you have option to not use it. So these are the examples. So let's do something real quick here. Let's do LS-USB to see if we have anything connected to the computer. So as you can see, I can see any USRP there. So when you are working with USRPs, the first thing you do, you run UHD find devices. So here we go. We have a USRP connected without any USB. So it has all the IP addresses for the channel emulator and things like that. And it says it's type USRP. So now I think we can start the experiment. Before that, let me show you the Q ground control. I have a port forwarded from OYO console, and now I can see the two vehicles on the ground waiting for me to upload a flight plan or my software to execute a plan. So let's do that. I'll just run experiment on all of the nodes. So this I will be using srsRAN LTE for just demo purposes, but you can run other experiments. I didn't configure anything on the channel side, just a simple channel for now to make things easier for the demo. On the tower side, I have srsRAN eNodeB, and I have the EPC there, also two AERPAW servers. And on the UAV side, I have the srsRAN UE in 4G, and then AERPAW clients. So I started the experiment, and let's see the screens I have. So I have a screen called radio eNodeB. So if you look at the logs, it starts like it's starting with the USRP, says multi-USRP, and then VUSRP TX, and it goes like that. And it has 50 physical resource blocks. It's running on 3.4 gigahertz right now, and 3.3 gigahertz. Let's connect our UEs. So this looking for connection thing is just trying to see if it's, oops. Okay, there's something happened. I'll just real quick stop the experiment. That's what I was fearing of. It always happens. As the eNodeB crashed. It won't take longer. I just need to reset and start again. I was trying to do change some settings before I do the presentation, so I think it might have affected it a little bit. As you can see, the vehicle heartbeats are resetted. Now I'll start everything from scratch. Yep. Running the experiment again. Connecting to the screen. And running this. Okay, got the UE connection. And then let's, don't do that. I'll just, what I will do is I'll just do a quick thing here. Vehicle scripts are already running. It should connect in a second. Okay, so I've connected the UE again, and then I will arm the vehicles. I think, yeah, the other one connected as well. So I armed my vehicles. As you can see, the altitude is changing, and the RSRP and SNR is changing accordingly. And as you can see, now my vehicles are taking off, and it's running on the UE and SRS UE, and the E0P is running. So I didn't reset it this time because you don't always have to reset it. It's just a spectrum environment, like the virtual environment we provide. So you can just, after you close it, you can just run it again. So it will work fine. So while I was running E0P or G0P, I could have also run something with Python UHD. So like some interference resource that might affect the performance of G0P and UE connection. So you have all the possibilities. As you can see, my vehicles are moving, and let's see. Yeah, I also have a connection. The data rate is changing, and yeah, that's pretty much all. Do you have any questions?
Is this sending traffic, like within the experiment?
Yeah, I'm running AERPAW.
Oh, just like,
Yeah, but you can, as I said, you can run any sort of traffic
and you
resource.
like put like a new radio flow graph on top of this and do some channel modeling? Or
Channel modeling is like we
not channel modeling, but you could like put distortion on the channel there.
yeah, you don't have to use GNU Radio. We are not also using GNU Radio on the background. The channel emulator and the virtual radio is developed by me, so everything is built from scratch. Aside from the virtual radio side, I would like to thank NI for like making the UHD open source so we can alter it. Yeah, and you can modify the channel model we have in the channel emulator. But if you want to like have an interference source, you can just do it with Python UHD or C++ UHD or any other application you may want to use.
How do you program the paths for the UVs?
So there are two ways. One of them is you can just create a trajectory on the Q ground control, and it creates a plan file. Or you can use a library called AERPAW lib, which allows you to give commands to the drone. So you can basically tell drone to go this point to this altitude with this speed, and yeah. So it's completely programmable. It's not just pre-planned.
What does the UAV do if the restarts?
You don't have to reset all the environment, all the vehicles. You see that like E0P crashed or something happened. You can, and you observe that you can just have a script that monitors the E0P and restarts it again in the digital twin or the real testbed. So.
The real test bed, what does the UAV do? Does it just stop? Or does it go?
Oh, it will go. It won't like, it depends on like what kind of vehicle script you wrote. Like if you are using the propellant trajectory, it doesn't monitor the E0P connection status or the network status. It just continues until it finishes the mission. But if you have an application that also checks the E0P connection or the metrics coming from your RAN software, and you can alter the trajectory based on the metrics you are getting, and then you can optimize the overall performance of your network. Any other question?
We have time for a couple more.
I said it for 40 minutes. I forgot it was 45 minutes.
Okay.
Yeah, according to me, I have 2 minutes. So.
If you want to show something else.
No, that was all. All of the vehicles landed. So.
What kind of customer base do you all have or expect to have for this kind of a test bed?
We expect researchers, or like if you have a hardware that you want to test with the mobility in a rural area. So that's kind of people and type of researchers we are kind of expecting. But yeah, if you want more information, you can contact the AERPAW, so they can provide more information. I'm just developing the digital twin and the other details.
All right, thank you.
Thank you for your question. So.
Okay, great.
Sure.
So are you going to open source the virtual?
Yeah. Yeah. Like I think next month or something like that. Yeah. Everything is going to be open source.
Great. Well, yeah. Thank you to Adam.
Thank you.